Here is something that should bother you, not in a vague, hand-wavy, philosophical kind of way. I mean, it should genuinely, physically bother you the way a splinter bothers your thumb. Because what I am about to tell you is not a metaphor. It is not a loose interpretation of the data. It is what the data actually says. And the data has been checked about 1,000 different ways, and it keeps saying the same uncomfortable thing. Take an electron. Shoot it at a wall that has 2 narrow slits cut into it. On the far side of that wall, you have a detector screen that lights up wherever the electron lands. Simple enough. You fire the electron, it goes through one slit or the other, it hits the screen. That is what your common sense says. That is what every instinct you have about how objects move through space says. And your common sense is completely, embarrassingly wrong. When you fire the electron and you do not watch which slit it goes through, it does not go through one slit. It goes through both slits at the same time. The same single electron, the same indivisible particle, goes through 2 separate holes simultaneously. And on the other side, it interferes with itself. The way water waves from 2 different openings in a break wall interfere with each other, creating a pattern of alternating bright and dark bands on the screen. Peaks cancel troughs. Peaks add to peaks. An interference pattern from a single electron. That pattern is the fingerprint of something that spread out like a wave and went through both holes at once. Now here is where it gets genuinely strange. Not graduate school strange. Strange in a way that should make you put down whatever you are eating and stare at the ceiling for a while. You decide you want to know which slit the electron actually went through. Fair enough, you set up a little detector right at the slits, a gentle one, something that just quietly watches and reports back. You run the experiment again and the interference pattern disappears. Gone. The electrons now behave exactly like little bullets. Each one goes through one slit or the other, and they pile up in 2 lumps on the screen behind the 2 slits, exactly the way buckshot would pile up if you fired it through 2 holes in a fence. The wave behavior vanishes the instant you look. You did not change the electron, you did not push it or deflect it or add any force to it. You just looked. And somehow the act of looking, the act of gaining information about which path the electron took, changed the physical outcome of where the electron landed on the screen. Now I want you to sit with that for a second without trying to explain it away. Because the instinct is to immediately reach for a mechanical explanation, to say, well, the detector must have bumped the electron, right? The photon you used to detect it must have kicked it sideways and scrambled the pattern. And for decades, that was actually a reasonable thing to say. It was wrong, but it was reasonable. Here is how we know it is wrong. Experimentalists are clever people. And they found ways to do this experiment where the act of detection is so gentle, so minimal, that there is no physical disturbance that could account for the change. You can set up what is called a delayed choice experiment, where you do not decide whether to detect which path until after the electron has already passed through the slits. You make the choice of whether to watch or not watch after the electron is already on the other side of the wall. And the electron, which has already made its journey, seems to have already adjusted its behavior to match what you are going to choose to do in the future. The pattern that shows up on the screen corresponds to what you decided to measure, even though the decision came after the passage. That is not a misprint. That is what the experiments show. Now let me try to give you some language for what is actually happening, because the language of everyday objects fails us completely here. When the electron is not being observed, it does not have a definite position. It does not have a definite trajectory. It has something called a wavefunction, which is a mathematical object that spreads out through space and encodes the probability of finding the electron in various locations if you were to look. It is not that the electron is secretly traveling through one slit and we just do not know which one. The electron genuinely does not have a fact about which slit it went through. There is no hidden answer waiting to be discovered. The electron is in what we call a superposition, meaning it is in some sense really physically in multiple states at once. Think of it this way. Suppose you have a coin spinning in the air. While it is spinning, you would not say it is heads or it is tails. You would say it is somewhere between the two, unresolved. Now imagine that the coin is not just unresolved in our minds because we cannot see it clearly. Imagine the coin genuinely has no face at all until it lands and you look at it. That is not a perfect analogy because a coin is a big classical object and is not actually in superposition. But the spirit of it captures something true about the electron. The electron has no definite location, no definite path until a measurement interaction resolves it into one. The wave function is not our ignorance about where the electron is. The wave function is what the electron actually is. It is a spread-out probability amplitude that travels through space, obeys a well-defined equation called the Schrödinger equation, and tells you the likelihood of various outcomes when you make a measurement. And when measurement happens, that spread-out wave function collapses instantly into a single point. The electron appears somewhere definite. Now here's the part that bothered me most when I first really thought it through. What counts as a measurement? What counts as looking? This is not a trivial question. It is one of the deepest open questions in the foundations of physics, and I will tell you plainly, nobody has a completely satisfying answer. Is it measurement when a photon bounces off the electron? Is it measurement when the signal reaches a detector? Is it measurement when the detector sends a signal to a computer? Is it measurement when a human reads the computer's output? Where exactly in that chain does the wave function collapse? The mathematics of quantum mechanics does not tell you. The equation that describes how quantum systems evolve is perfectly smooth and continuous and deterministic, and at no point in that equation does anything collapse. The collapse is something we bolt on from outside, something we say happens when measurement occurs without being able to say precisely what measurement means at the physical level. Some physicists have taken this seriously and said maybe nothing ever collapses, maybe the universe just keeps splitting into branches, one for each possible outcome of every quantum event, and we are always in one branch without being able to see the others. That is the many worlds interpretation, and it has some serious thinkers behind it. Others say the collapse is triggered by some kind of interaction with a large classical environment, which is the decoherence picture. And that actually explains a lot without invoking consciousness or anything mystical. Others have tried to build theories where the collapse is a real physical process that happens at some scale. But here is the honest situation. All of these interpretations reproduce the same experimental predictions. They all give you the same numbers when you calculate where the electron lands. The experiments cannot distinguish between them. What we disagree about is not the mathematics and not the predictions. We disagree about what is really going on underneath. We disagree about the story. And that should tell you something important about the nature of what we know and what we do not know. We have an extraordinarily precise and successful theory. Quantum mechanics is the most accurately tested theory in the history of science. The predictions it makes have been checked to 12 decimal places in some cases, and they match every time. But the theory comes with this strange gap at its center, this unresolved question about what a measurement is and why the act of acquiring information seems to affect physical reality. Let me push on the interference pattern a little more, because there is another layer here that people often miss. Suppose you run the double-slit experiment with electrons and get the interference pattern. Now suppose you fire 2 electrons through at the same time. Does each electron interfere with the other? The answer is no. Each electron interferes with itself. The interference pattern builds up 1 electron at a time, 1 dot at a time on the screen, and only after thousands of electrons have landed do you see the full pattern emerge. If you watch the screen as the electrons arrive one by one, each one lands in a random-looking spot, but those spots are not truly random. Each one is drawn from the probability distribution set by that electron's own wave function, a wave function that passed through both slits. The pattern is baked into each individual electron's behavior. The electron is somehow spread across both paths and interfering with its own alternative self. Now I want to push on something even more fundamental. What the double-slit experiment is really telling us is that electrons do not have trajectories in the way we imagine. A trajectory is a line in space that an object follows over time. You can draw the path of a baseball from pitcher to catcher, and there is a single definite line. But for an electron moving from source to screen, there is no such line. The electron does not take a path. It takes all paths simultaneously, and these paths add up and interfere with each other to produce the final probability of landing somewhere. Richard Feynman himself developed a beautiful way of computing quantum mechanical answers based on exactly this idea. You add up the contributions from every possible path the particle could have taken, each one weighted by a phase factor. The answer you get when you sum all those paths matches the experimental observations perfectly. This is called the path integral formulation, and it is one of the most hauntingly strange things I know about physics. The reason a ball follows a straight line through the air is not that it chooses the straight line. It is that all the nearby paths interfere constructively, while the paths that deviate strongly cancel out. The classical path is the one that survives the interference. The electron has no such classical path to survive to, and so it spreads. Here's one more thing worth understanding about why this measurement problem is so unsettling for physicists rather than just for curious outsiders. In classical physics, the act of measuring something is in principle harmless. You can imagine a perfect measurement that disturbs the system arbitrarily little. You can imagine knowing both the position and the velocity of a particle as precisely as you want. The universe allows it in principle. But in quantum mechanics, there is a hard limit built into nature. This is the Heisenberg uncertainty principle. And it is not a statement about the imperfection of our instruments. It is a statement about nature itself. The more precisely you pin down where a particle is, the less defined its momentum becomes. And this is not because the measurement disturbed it. It is because position and momentum are not simultaneously real in the way we normally think of things being real. They are complementary aspects of a quantum object that cannot both be sharp at the same time. So when you set up the detector to watch which slit the electron goes through, you are doing something that quantum mechanically entangles the electron's path information with the detector. And once that information exists in the world, even if you never read it, even if you destroy the detector, the interference is gone. The potential for interference depends on there being no information anywhere in the universe about which path was taken. The moment a record exists, even a physical record that no conscious being ever reads, the wave behavior disappears. That is what all the careful experiments show. I will tell you honestly, and this is something I feel comfortable saying because the physics backs it up. Nobody understands why this works. We understand how to use the theory. We can predict the outcomes of enormously complex experiments with staggering precision. But when you ask what is the deep story, why does information about the path destroy interference? What is really happening when the wave function collapses? You get silence from the equations. The equations work. The interpretation is incomplete. And I think that is worth sitting with, not as a failure of science, but as a sign that nature is stranger than the universe of common sense we walk around in. The atoms in your hand right now are behaving quantum mechanically. The electrons in the chemical bonds of your body are spread out in probability clouds, not sitting at definite locations. The solidity of the world you feel is a kind of emergent average, a classical behavior that crystallizes out of trillions of quantum uncertainties all averaging together. Dig down into the fine grain of matter and you find something that does not quite obey the rules you grew up trusting. That is the double-slit experiment. That is what it tells you. Not that physics is mysterious in a cozy, hand-wavy sense, but that the universe has a specific, mathematical, experimentally confirmed strangeness at its foundation, and we are still working out exactly what to make of it.